Hello and welcome you all to the lecture number 15 of this NPTEL course titled Electroweak Interactions in the Standard Model of Particle Physics. And today we are going to talk about something very important, essentially continuing from what we discussed in the last lecture. We are going to carry on the discussion on the symmetry transformations and groups. So, this is something which plays a very important role in constructing the Lagrangian and deciding what kind of interactions that will be there. So, this is something which is going to play a key role in what we are going to do in the main part of the lectures, but this is a preamble to set the stage and to set the notations like what and how the symmetry transformations form something called groups and what are the generators, how we can do the representations. So, this will be a set of 2 lectures and we are going to start today. Okay. So, let us get started. And so, the first point that we sort of collect is the following, that suppose we are talking about this translation operator. Now, when we are talking about the translation operators, let us denote it. So, for example, T A, which is acting on the space time point, suppose x, what does it do? This basically translate your position coordinate from x to x plus a, correct? So, similarly, I can also think of time translation operator, right, I mean which translates the time from T1 to T2, something like that. I can think of rotations. So, this is another classic example. So, which rotates, suppose your x1, x2, x3 coordinates to r theta. So, this is the rotation matrix by which by which you actually rotate. So, if you are just rotating it by an angle theta, suppose you know how to write it. I think this is exactly how we should write cos theta minus sin theta, and this is sin theta cos theta. So, you remember that suppose if you think of 2-dimensional coordinate system, suppose if you have x and y sitting here, right, and then you rotate by an angle theta, right. So, you go to x prime and this is your y prime. This is precisely how you relate. X prime will be x cos theta minus y sin theta, and your y prime that you define will be essentially x sin theta plus y cos theta, right. And this is essentially a rotation about the z axis. So, z remains the z. So, this is precisely how we can then parameterize the rotation, like x bar prime goes to r theta into x bar. Bar means the vector, basically x1, x2, x3 rotates in this one. So, this is the rotation about the z axis, and you can really do the generalization for rotation for other things also. Now, the point is that we have to transform, or rather we are interested in transforming the quantum states or quantum fields rather, so to say, because that is what our Lagrangian is constituted of. And there I actually have to ask that what kind of form this transformation operators actually should take up. Now, first thing that we note is that for transforming the quantum states, because the quantum states resides in the Hilbert space, we need operators which actually acts on Hilbert space. Now, what is Hilbert space is something that you should ask ChatGPT and get me an answer by the next class. Let us now try to see a translation in space time for these different quantum states. Okay. So, for example, if I take this operator u a acting on x and transforming it to a position x plus a. So, this is how I define the translation in space. Okay. So, u a x taking you to x plus a. You can say that this is basically transformation that takes your particle from position x to position x plus a. Now, the point is the normalization that we must resort for the quantum states, that is independent of the position. So, it is independent of whether you are at x or at x plus a. So, therefore, you must resort to x inner product with bra and kit must be equal to the inner product of x plus a, right. So, this is x plus a, and then you can say, okay, all right. So, if x plus a is obtained by u a acting on x, then the one which will be operational to give you the x plus a brass must be u dagger a. And the point is that this is simply, as we said, that this must be equal to the inner product of the x itself. So, this basically tells you that u dagger a u a must be equal to 1, and this is what is referred to the property of these transformations as unitary transformations. Okay? So, this is the term unitary. So, if you think of this like a matrix, a complex matrix, then basically you can say a dagger a is equal to 1 is what the property that you actually refer to those matrices as unitary matrices. So, therefore, you say that okay, this translation in space that you are actually doing, that will be an unitary matrix. Now, it is not very difficult, but we can also see that there are some other properties that they also follow, like you translate the position by A and then by B is equivalent to make the translation by an amount A plus B. So, therefore, you can say that the successive operation of u A and u B is equal to u of A plus B, and this is sometimes which is referred as the closure property. And then there is another important point, that if you translate by 0 units, so to say, then you actually get an identity matrix, because you are not doing any kind of translation at all. And then you can also do something which is like reverse translation. So, you translate to x plus a, and from there you take a reverse transformation of by minus a and return back to your previous position. So, that is like an inverse. So, this is called the inverse. So, you have something like a closure property, you have something like an identity, you have something like an inverse, and this basically tells that these transformations actually form what we call a group. And this brings me or brings us to a question, what is a group? Right. So, many of you perhaps already know, but it is good to reiterate that a group is basically a set G that has an operation. Suppose let us call this operation dot, so that if you have two elements belonging to this set, let us call A and B, which belongs to this group G, and when they actually have that kind of operation amongst themselves, like A dot B, A dot B, this operation will take you to an element which belongs to that set itself, and this is how precisely we write it, that A dot B will give you an element belonging to that set itself. So, then you say that I can form a group if there are some 4 other credentials which are also satisfied. Now, first of all, as we said that for each A and B belonging to G, if A dot B matlab it does not have to be the vector dot product or something. You can think of numbers, then these numbers can have operations like addition or subtraction or multiplication. If you think of matrices, you can think of this operation like matrix multiplication, so something like that. So, what operation is this depends on what kind of set that you are trying to probe its properties, and there has to be some mathematical operation that you can do, that you can rather define on this set of objects. And the point is, if you do an operation between 2 elements belonging to this set, if it takes you to a third belonging to the set, that is what is referred to as a closure property of those elements. The second point is, if you have 3 elements, suppose A, B and C, and then you claim that it's immaterial in which order I do this operation, like A operated on B dot C is equivalent of A dot B dot C. This is what is called an associative property. Okay. So, this must be also followed. And the third point is very, very important, and it says that I must possess something like E, by which if I operate on any element of this group, then it actually gives me back the same element itself, and this is something that we all know, this is our identity. So, we do not have to go far, we have the real number set itself as an example at hand. For example, for real numbers, if you think closely, what is the identity? Well, 1 is that the identity? Now, of course, if you think of the operation as a multiplication, then 1 is definitely the identity, because 1 into 2 is 2. 1 into 5 is 5, and so on. So, if you multiply anything with 1, that is going to give you the same number. But what about addition? If you do add 1 with something, it does not take you to that same position. So, in that case 0 will be the identity. So, it depends on what kind of operation that you are doing and what kind of identity that you have. The same set of elements can form a group under different operations, like the real numbers, as I just gave you an example of. Then there is another important point that you must resort to in order to form a group, is that for each element A belonging to G, there must be an A inverse belonging to G, so that when you do operate A with A inverse, immaterial of which direction, A dot A inverse or A inverse of A, this brings me back to the identity, right. So, and this is what is termed as an inverse. So, each element must possess an inverse to form a group. I mean, if you have to really say that this has to form a group. So, therefore, these are the properties that we need to satisfy. Once again, let us think in terms of real numbers. If you have plus 1, so then you must have a minus 1, so that plus 1 and minus 1 adds to 0, which is the additive identity of the real number. So, for example, if you have 5, then minus 5 is the inverse of 5 in terms of this addition as an operation. On the other hand, 5 will have an inverse of 1 by 5, right. So, that will be when it multiplies, then it gives you the identity, which is 1 when we consider the operation to be the multiplication. So, therefore, you can see what are the things that forms a group. So, we will take up a few exercises in our tutorial to see, I mean, to check different examples of what forms a group and what does not. Now, there is another important point that I would like to mention. Well, I mean, this is a kind of thing, this is an additional property, that if you have this A dot B is B dot A, and this is always independent of whether you are operating with the identity or with the inverse, because the operation with the identity and the inverse are always like A dot E is equal to E dot A, or A dot A inverse is equal to A inverse A. So, that is always follows this order, but it is not necessary that you always have to have A dot B is equal to B dot A. For example, if you think of matrices, the question whether the matrices form a group or not, I mean whether all n cross n matrices form a group, the answer is no. However, that is something that you should work it out, but it is of course that when you do matrix multiplication, the order becomes very important. A dot B, A multiplied with B is not equal to B multiplied with A. So, therefore, if you think of matrices, this property is never followed, but whenever this is followed, this is called, or the group is called, an abelian group. Now, this is something that we are going to take up, and this word is going to come back again and again when we actually talk about some transformations on the quantum fields, which we will be writing the Lagrangian and the interactions, and which will be bestowed with the properties, or saying that okay, this is my electron, this is my positron, this is my photon, which will be carrying the interaction between blah and blah. So therefore, in those cases, this terminology that how we can restrict their interactions just to be exactly the way that nature wants, we will bring back this symmetry arguments and this abelian or non-abelian nature. So that's why I am just defining the terminologies here. Now, there is an interesting thing that I explicitly mentioned here, that for example, the parity transformation, like parity transformation, something that we have already talked about, that you basically have a reflection symmetry like x going to minus x. This together with the identity transformation, which is like you do not transform. So, this is the identity you can imagine, and this is the non-trivial transformation that you have. These two elements will actually form a discrete group which is called Z2, and this group is also heavily used in doing particle physics. Particularly, we will come back to the very last lecture when we talk about the possibilities of explaining the dark matter of the universe, and we need some symmetry arguments to stabilize it, and we will come back to this symmetric group of Z2. But before that, you must confront this group and show that all the above properties which I just talked about is satisfied by it, and so this forms a group. Okay. So, having said that, let us come to some more properties, like the translation which we started talking about, and for which we found out a kind of property, like it has some special property of what is like u dagger A is equal to 1 on top of the closure, having an identity, having an inverse, having the associativity, etc. This actually forms a group, not only a group, but actually a unitary group. Okay. And this also have another important property, which for example, the previous one which I just mentioned, that reflection symmetry does not possess, is that it has actually infinite number of elements, and this group is continuous and differentiable, and this was classifies to something what we call a Lie group. Okay. So, I am not going into very formal definitions of all these things, but there is a beautiful book by Morton Hammermesh. If you want to go back and take a look into those, you should actually. Okay. So, because this translation forms a special group which depends on a vector A and which is like continuous, differentiable, and therefore, you can generate infinitely many elements for this group, and so therefore, this is the Lie group. And we identify what is the identity. I mean, so U0 which is called the identity, UA UB will always take you to UA plus B, which is the closure, and similarly you have the associative property followed, and you have the inverse. The inverse is the dagger, U dagger A is equal to U inverse A, which is equivalent of saying that U of minus A, which always brings you back to the identity, and that gives you the presence of inverse. Okay. So, this follows all this property, and you can very well say that this translation operator that we are talking about forms a Lie group. Now, I would like to see an interpretation of UA more closely. Can I explicitly, because here, I mean, I have expressed it all vaguely. I mean, what is the mathematical operation of UA that we are talking about, which takes you from the ket x to x plus a? What exactly? How exactly I can think of it in terms of an operator? But in order to do that, let me think of the position operator. Now, position operator, let us call it x hat. What does it do? That when you operate this position operator on any state, say for example, x hat, the position operator acting on any state x will give you essentially the value of that position. So, this is what it does. So, now the point is, according to our definition, what we have said that UA, when it acts on x, it will take you to a ket like x plus a, correct. Now, what happens if you now operate this x hat on UAX? This is simple, because UAX have already taken you to x plus a. So, when x operates on this, what we are going to get? We are going to get x plus a, x plus a. So, we are going to get the value of x plus a. Okay. Now, let us operate with u dagger a on the same thing. So, you know, x plus a is a number, so the operator does not work on this. So, basically I can bring the x plus a here, and it will be u dagger a of x plus a. Now, can you tell me what happens when I operate u dagger a on x plus a? It is essentially the inverse operation, right. So, inverse operation means that I am going to bring this state back to x. Okay. So, this basically means that I am going to have x plus a x. Now, let us think of having this operator x plus a, position operator x plus a acting on x. What exactly it is going to give you? It is going to give you x plus a x. So, therefore, you basically mean that this last operation that you actually did is equivalent of saying that this is x plus a operator acting on x, correct. So, now if you compare these two sides, like this one, this operator and this operator, you are basically saying then u dagger a x u a is nothing but the operator x plus a itself. So, now we have a vision slowly building like what kind of operator u a is. We are not yet there. So, the space translation operator can be thought of the transformation of an operator x instead of the acting on the ket itself. So, we are now visualizing what kind of operator that we can actually form for this kind of translations, spatial translations, but we have not yet reached there. So, let us consider a special case of psi x where psi x has to be a number. So, therefore, I define this to be x dot p, if I may say. I mean it is the inner product of x and p. So, now what will happen to psi of x plus delta a? This will be, I can Taylor expand this, and this will be essentially psi x plus del psi del x into delta a, and then there are higher order terms which I for the time being ignored. Now, I would like to remind ourselves that this is a we are thinking of the wave function to have only one variable in it, which is the x actually. So, in that case I can think of the momentum operator a p is equal to minus I d dx. Now, this is something that you recall. Why this was so? This is something that is the starting point of all this business that we are doing, which is the first quantization principle that we actually we studied. This is actually minus x p commutator is equal to minus I h cross. So, when you try to express the momentum operator in the position space, it should take the form of minus I h cross del del x. The only thing that we are doing, that we are adopting to natural units where I have used h cross equal to 1. So, the p operator should be written as minus I d dx. Therefore, now if you go back to this relation, then you can say okay, psi of x plus delta a, I can rewrite it as psi x plus I p, right, delta a psi x, or in a sense I can say that psi of x plus delta a is nothing but I 1 plus I p delta a psi x. Now, if I ask you that if I take this transformation successively again and again to capital N number of steps, so that this transformation to x plus delta a, it takes you to x plus a. Okay? And so, therefore, I can simply say that psi of x plus a, where A is accounted by this delta A steps, capital N number of times, where N is repeated almost to infinity, then I can simply say that psi of x plus A is equal to limit n tending to infinity 1 plus I p delta A whole to the power n, right. So, I have done it capital N number times with n tending to infinity, and this is what we have. Now, can you tell me what exactly this means, limit of n tending to infinity 1 plus I p delta A whole to the power n. Now, I would like to say that this is nothing but e to the power I p. Now, if you are not very happy with this expression, I would like to urge you that you go back and actually see how exactly this equivalence can be brought up. Okay? But you can, many of you can actually see that this will give you n p a plus then this expansion and so on. You just simply Taylor expand all these terms, you get those infinite series, which is simply e to the power I p dot a psi x. So, however, we want to translate the entire quantum state through a distance a, not how it evolves over a distance a, right. So, therefore, let us go back to this definition once again, psi x equal to x p. So, therefore, what will be psi of x plus a? Psi of x plus a will be simply x plus a p, right. So, psi of x plus a, we have already confronted that it is something like e to the power I p dot a psi x. So, this is what we have found out, but which is simply as we just borrowing from this expression above, this is e to the power I p a psi x. And on the other hand, if you have defined that you take your operator, or rather your operator will, what was the definition? So, from our definition we had like u a when acts on x will take you x plus a, right, or in a sense if I write it in terms of bra. So, this is x plus a equal to u dagger a acting on x, correct. So, therefore, if you substitute this back here in this expression, what you have essentially something like this. This is essentially x u dagger p, and here I have brought the u dagger out here and said that this is u dagger x p, and once again psi x is defined as x p, and so this gives me a form of u a. So, what it says that u dagger is e to the power I p a, that means u a is e to the power minus I p a. So, this is a pretty interesting one, that finally we know what kind of operator that u a has to be, so that it translates you from x to x plus a, correct. So, this is very interesting. Now, I would like to consider time translation. Now, in time translation kya hoga? I am basically saying, or rather considering the wave function to transform from psi of t plus psi t to t plus delta t a. Now, once again we can expand it in the Taylor series, and so therefore, this is psi t plus simply d psi dt into delta t a plus blah blah blah. And now, I would like to remind myself that the Hamiltonian operator with once again h cross equal to 1 was I del del t. You all remember the Schrodinger equation, correct? And the Schrodinger equation was what? It was the quantum form of the classical relation E is equal to p square by 2m plus v, right. And from there also you can see the quantum analog of the energy operator, which is nothing but I del del t. Of course, we had those explicit h crosses sitting over there, but now we do not have them. But nevertheless, everything remains the same. So, now let us try to write this above expression in terms of the h operator. How can I do that? So, this is minus I, right, h delta T A psi T, correct? So, and I am dropping the other term. So, therefore, you can simply say this is nothing but 1 minus I H hat delta T A acting on psi t. And similarly, now I can say that I can do this step infinitely many times with capital N number of times, then psi, and to take you from psi of t to psi of t plus T A. So, therefore, psi of t plus T A will be limit n tending to infinity 1 minus I H hat delta T A whole to the power n. Now, once again, what exactly this quantity is? This is nothing but exponential minus of I H T A acting on psi t. So, therefore, now we first have the relation of how psi t plus T A is related to psi t, and you basically say that this is the transformation via this e to the power minus I H T A. And following a similar argument like the way that we did, so we previously had this expression like psi of x plus a is equal to e to the power I P A psi x. So, if the operator u a takes you from position x to position x plus a, then that u a operator we found out to be e to the power minus I P A. And here we said that psi of t plus T A is e to the power minus I H T A psi t. So, if there is an operator u t which will take you from 0th time to time t, then basically we can identify that u t a operator, and this will be similar to the previous argument. This will be simply like e to the power I H T A. Now, what I can do, that I can put the space and time together, and I can say that this u a operator which acts on the 4 space time points, this will have e to the power I H T A into e to the power minus I p dot a, and you can simply say this is nothing but e to the power I p hat dot a. Here I actually define the p hat to have the 4 components with the Hamiltonian h and the momentum operators p. So, this is what happens to the space time translation. So, this is exactly how the space time translation operator looks, and we argued that this actually form a group. Now, let us look into another very important transformation which are called the rotations. Okay. So, let us propose that the rotation is like takes you from a state p to state p prime by a rotation of u theta. So, this is how I actually denote it, that p prime is equal to u theta p, or which you can define that this is actually the rotation of the p space by matrix. So, this is a state which has been rotated, right. So, like the way that we defined the translation, like you are going from position x to x plus a. Similarly, I define a rotated state by r theta p. So, basically u theta when acts on the state p gives you the rotated r theta p. So, this is once again the case, and similar to the previous arguments, one can verify that u dagger theta, u theta must be equal to 1 unity, and you have all the properties of a group like unitary, identity. So, you can always think of transforming rotate by 0 units, so which gives you an identity. You can always think of reverse rotation, which will bring you back to the identity. You can always think that when you are rotating by theta 1 and theta 2, it's equivalent of rotating by theta 1 2. So, all the properties of the group is actually satisfied once again, and this also has infinite elements. These are continuous, have a derivative. So, they are Lie groups. So, they form a rotation group. Okay. So, you have a rotation group which is another kind of Lie group, and you can once again check the unitarity or u dagger is equal to 1 explicitly. Okay. So basically, therefore, I have the examples of translation. So the point is, I found out first that u dagger a x u a will be equal to x plus a, and here I do not define or derive that explicitly, but I rather argue that when I have that u dagger theta acting on the, because I am talking here in terms of momentum vector or operator. So this momentum operator p u theta, that will essentially rotate your p state to r theta p. This is what we envisage. So this is something that I have not derived, but you can try deriving it. But now with the help of the properties that we have defined, can we find the explicit form of the rotation operator by which you can actually rotate these states, okay, which is another symmetry transformation. So for that, what we did, that we would like to expand psi of theta plus delta theta z by Taylor expanding, and we say that this is psi theta plus d psi d theta z delta theta z, and then I use once again this identity that j z hat is equal to minus I d d theta z, and this represents the rotations are generated by something like angular momentum operator, right. So therefore I can now get back to this expression of psi theta plus delta theta z, and this is going to be nothing but you can say that this is nothing but I j z delta theta z acting on psi theta. So once again, following the same logic, if I do this exercise capital N number of times with limiting n going to infinity, so this is basically limit n tend to infinity 1 plus I j z delta theta z whole to the power n, and this is what? This is essentially e to the power I j z theta, or something you can call, or theta z if you want to say. So this is what parameterizes the rotation. So following the same logic that we actually had to identify the corresponding form of the operator, what we can say. So if psi theta is going to psi of theta plus theta z by this operation e to the power I j z theta, what will be your u of theta z? You say that this is nothing but e to the power minus I j z theta. This represents a rotation about the z axis, and if you have to generalize this form of u theta, then you will say that this is e to the power minus I, you can simply say that this is j dot theta. Okay. So this is how you can basically parameterize the rotation operators. So this is also a group. I will give you more examples of what are the unitary groups, and we come to a point what is called the representation of the groups in our next lecture. So today we are going to stop here, and we are going to take it up in the next lecture. Thank you.